Okay, so in this video, we're going to be looking at standing waves, where the wave is fixed at one end and open at the other. Now, don't get scared by the equation that you can see here. We're going to talk about that. We're always going to draw the pictures, and then you can kind of go from there and figure out how to solve the problem. Now, fixed at one end and open at the other is a little different. So what I want to show you here in this wave applet right here is that if I start it and I change this to free from one end, I'll start it. Okay, so just like before, you can see that the wave comes in. Now it comes in as a crest and then a trough, and it's a periodic wave, right? So you can just imagine that you're vibrating a string, or you're vibrating a slinky, or whatever the case may be, some surface, some material, some medium. You vibrate it at a periodic rate. Then what you'll see is you get these waves coming in. Now, when they hit a free end, remember that the wave will go, watch, it reflects on the same side. So the reflected wave comes back on the same side. We learned that before when we were first learning about waves. And what you'll notice is that, look here at the free end, you get a crest and a crest meet. Well, let's look at the resultant, or the superposition. Wow, look at that, a big wave. If we resume it, that wave then destructively, then constructively, then destructively, constructively, destructively, constructively. You get the idea. Let's look at what the picture looks like. Okay, here's what it looks like. You've now got a standing wave. Now, this one, you can't tell, but this is open at both ends. This would be like an air column that's vibrating or resonating as with a standing wave. And there's an antinode at the end. And here there's an antinode at the other end, because this is fixed. Oh, sorry, this is open at both ends. Now it says from a free end. So now what you would have to realize is that if you ignore this little part here and you were holding it right at this node right there where I'm clicking, then there would be an antinode, or sorry, a node where you're holding it and vibrating it. And then there would have to be an antinode over here. Okay, so that's the key. That's the most important part of this. So let's take a look. All right, first resonance length, the fundamental frequency, or the first harmonic, F1. Remember, we know that that F2 is 2 times F1. F3 is 3 times F1. And F4 is 4 times the fundamental frequency. So the frequency goes up, the wavelengths get smaller and smaller. Okay, at the first harmonic, you would have to, like, imagine this is like if you hold a pencil and you just do this. Okay, and if I turn it sideways, you can kind of see I hold the pencil here, and you're going to get an antinode at the one end and a node at the other end. And so it's tough to draw, but you would see that you get something like this. Okay, it can't, or like something like if you see an aerial on a car or a tree swaying, trees often sway like this. Like they'll just vibrate back and forth. Telephone poles, all kinds of things vibrate at the first fundamental harmonic in nature all the time. And if you just drive by on a windy day and look at anything like a light post or a stop sign or something like that, they always will vibrate back and forth. And the antinode at the top and the fixed position at the bottom is the node. So it's always at that fundamental frequency, or almost always. And then there's an antinode here, and there's nothing in between. So it's just vibrating like that. Now, at this, you would say, well, how many wavelengths are in there? And so this really bothers some people, but it's okay. This hasn't even come back down. This is a massive wavelength. It's huge, right? It's like vroom, vroom. It's got to go all the way over here. In fact, it's got to go 4 distances, because this is only 1/4 of a wavelength. That's a lambda. That's 1/4 of a wavelength, because it's got to go up, back down, all the way down, and back up to produce 1 full wavelength. So it's really big, right? So whatever this wavelength is divided by 4, and that tells you the distance from this node to this antinode. Okay, so that's the case. Now, if you want to use a formula up here, L1 equals 2 times 1, which is 2, subtract 1 times the wavelength over 4. 2 times 1 is 2, 2 minus 1 is 1. You get lambda over 4. So that's the equation for this one. But you can just say, well, it's a quarter of a wavelength. All right, the second resonance length, let's take a look. Second resonance length, there's going to be, it's going to be L2. 2 times 2 is 4. 4 minus 1 is 3. So it's 3 lambda over 4. So it's 3/4 of a wavelength. And so what we're going to see is that there's going to be half a wavelength, like this, and then a quarter. This is the fish one. It's going to be a node, an antinode, and an antinode. Why is this closer? Well, because there's only a quarter. This is half of a wavelength, so there's only a quarter. So that's a quarter, quarter, a quarter. Oh, if you have 3/4, a quarter, a quarter, a quarter is literally 3/4. I don't know. You can't even change that any other way. See? Quarter, 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 3/4. Okay. Or a half and a quarter is 3/4. So you would say, well, there's half a wavelength and a quarter, and 1/2 and is 2/4, and 2/4 plus a quarter is 3/4. I don't know. I can just keep saying it all different ways. Or 0.75 wavelengths. Notice it got smaller. There's now the full wavelength is actually just to here, whereas this one, the full wavelength was huge. So it's decreased by half. And you can see, like, that the wavelength's gotten smaller, so the frequency has to go up to do that. At the third resonance length, you're going to now think, well, let's use the formula. 3 times 2 is 6. 6 minus 1 is 5. So it's 5 lambda, 5/4 of a wavelength. Well, what's 5/4 of a wavelength? It's 1 1/4 wavelengths. So there's going to be the quarter at the end, and then there has to be one full. Oh, that is really bad. So there's got to be one full one. And I messed it up. There you go. You can fix yours and make it look better. It's totally not right, my proportions. These two should have been closer down here because the last one's a quarter. So this clearly doesn't look right, because how could this be a half and that's a quarter? So clearly I did not draw that correctly. But regardless, you get, and that's because we just keep adding nodes based on the ones that we go up. So that's antinode, 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 node, node, node. 1 1/4 wavelengths. 5/4 is 1 1/4 wavelengths. And if you want to write that as 1.25 lambda. Notice can you see what's happening? Quarter of a wavelength, and then it goes up by half of wavelengths every single time because we're adding in these additional ones. So so you can see that's half a wavelength, so we added half a wavelength. 0.25 times 0.5 is 0.75. 0.75 plus 0.5 is 1.25, so on and so forth. Okay, the fourth resonance length, L4. 2 times 4 is 8. 8 minus 1, so 7 lambda over 4. Again, we went up by half a wavelength. So there should be, in this case, you would have to draw another one in here. So there should be 3. So that's probably better than what I did before. It's more representative of that quarter hanging out there at the end. Okay. Antinode, 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 node, 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 node. There's a destructive interference, constructive interference. And we now look and we see we've got 1 1/2 1/4. Okay, so what is that? So L4 equals 7 lambda over 4. Well, what's 7 lambda over 4? Like that's something that you figure out. You just is 1 point. Well, it's easy. It's just 1.75 wavelengths, right? And you just remember because it's 1.25 wavelengths, you add another half. We've added another half. And notice how small these wavelengths are getting. They're cramming up. Like this wavelength at the beginning was huge. If we keep the material the same length, whether it's the pencil, I can't get this thing to vibrate at the second harmonic because it's too rigid. If it was like very flexible, you could get it to vibrate at all these different harmonics. And as you increase the frequency, you decrease the size of the wavelengths. Like look how small this wavelength. I mean, I can't even draw it. It's huge. This one I can't even get to it because it's all the way over here. This one I can draw one wavelength. It's right there, and this one again, one way. Now I drew this wrong, the one above it, right? Because this one, these two circles or the node should have been closer over here. And you would have seen that this wavelength here is just getting smaller and smaller. If I went to the 5th, the 6th, the 7th, the 8th, it would just keep getting shorter and shorter and shorter and shorter. Okay, so let's take a look at the example. So we have a metal rod fixed at one end, vibrating at the second harmonic, has a measured wavelength of 20 centimeters. So wavelength, 0.2 meters. The rod vibrates at the second harmonic 40 times every 2 seconds. So that's 20 hertz. And it says L2 is our resonance length. It says if the rod is vibrating, calculate the speed of the wave. So we're going to try and find the speed of the wave. And we know that the speed of a wave is frequency times wavelength. And so this question, I guess, is fairly simple. And we have to calculate the length of the rod, right? So there's two parts that we're trying to look for. We can find the speed of the wave in no time. We already know the frequency and the wavelength. So the speed is easy to get. So the frequency was 20 hertz. The wavelength was 0.2. You multiply 20 times 0.2, you can probably do it in your head, is simple, 4 meters per second. Okay, so that's the speed of the wave in this material. So it's vibrating at this harmonic right here, the second harmonic. You would typically draw this to find out that there's a half and a quarter to give you 3/4 or 0.75 wavelengths. Or you can use the equation. Okay, so finding L2, right? So to find L2, you would just go, you could draw this picture since we know it's this situation right here. That's important to recognize. It's this situation. You would just go 2 times 2 times 2 minus 1 lambda over 4, or draw the diagram and you would see, oh, that's just 3 lambda over 4 is L2. Now, I already have the wavelength. The wavelength was 0.2 divided by 4. So you go 3 times 0.2 divided by 4 tells us that the object is about 0.15 meters in length, which makes sense because if the wavelength is 0.2 and it's resonating this frequency, look at the wavelength's 0.2, which is all the way out here, but the rod is only this long, which means that it has to be smaller. So it's got to be 0.15. And in fact, that's 3/4 of 0.2. Okay, so that's all you need for that type of question. Again, you just got to recognize which formula to use and which diagram that you should draw that goes with it.